All right, so I'm going to continue with what I was discussing last time, Shintani's method, and today what I'd like to do is really make explicit the connection between Shintani zeta functions and Stark units. In particular, how one can use Shintani-type methods to give explicit yet conjectural formulas for Stark units, which in particular are amenable to computation and verification of these conjectures explicitly. Let me begin by recalling a few highlights of what I discussed yesterday. So the setup was we take a matrix A, so part 0 is the recall. So let's take a matrix A with in M n by D of C with the real part of all of these matrix entries being positive. This was an analytic assumption we needed to achieve the meromorphic continuation. And let's take a vector x in R to the D with non-negative coordinates, and I'd like to make sure that this vector isn't the zero vector. And the Shintani zeta function associated to these data is defined to be the sum over D tuples of non-negative integers of the norm of the vector A times x plus k to the minus s, whereby the norm of a vector, I just mean the product of its coordinates. And this series converges absolutely in the region real part of S bigger than D over N. And we worked hard yesterday to meromorphically continue this zeta function beyond this right half plane. And we used Shintani's trick to do that. It's not easy to find you can't find a contour integral representation for this whole zeta function like you could say for a Hurwitz zeta function or the Riemann zeta function, but you can express it as the sum of n contour integrals and meromorphically continue each one of those. So what we had was that zeta of AXS is the sum of n pieces, one corresponding to each of our coordinates, and I called each piece zeta I of AXS, where I was able to express each of these pieces, Zi of AXS, as a contour integral. So this was something just a shorthand, Cn of S times the integral over the Hankel contour starting at infinity of the integral over now the product of n minus 1 Hankel contours beginning at the point 1 on the real axis of this product of exponential functions, g of uy evaluated at yi equals 1 times the product over all variables distinct from I of yr to the s dyr over yr. And there's still something undefined in this. There are still two things undefined in this equation. Cn of s involves a gamma factor, and this arose from iterating Euler's integral n times, one for each variable, and a few exponential factors which account for the difference in the argument along the inbound and the outbound branches of the Hankel contour. So recall the Hankel contour looked something like this, where we approach the point epsilon along the real axis, revolve around the circle of radius epsilon, and then go back out. And along the inbound branch, we define the argument to be 0, and along the outbound branch, we define the argument to be 2 pi, just to make sure that everything was continuous as we travel along the contour. And this function g that appears in the integrand is a product of j pieces, each of which we got from summing a geometric series, And these terms are e to the t times aj times 1 minus xj divided by e to the t aj minus 1. N minus 1 here. Thank you. That's right. All right, so these factors are there because the argument changes by 2 pi when we between when we go in and when we go out. And this is this expression is valid for epsilon small enough. Okay. So this picture is good for more than just the meromorphic continuation of the zeta function. It's also useful if you want to evaluate the zeta function at negative integers or non-positive integers, which we're very interested in, especially the point s equals 0, which is the one that's of interest in particular for Stark's conjecture. So let me discuss the values of zeta of AXS at non-positive integers. And the technique we use to get formulas for these values is just residue calculus and this integral representation. So let me give you the formula, and then we'll maybe work out one example. The value of Zi of AX at the point 1 minus m, where m is an integer at least 1, is given by the following quantity, minus 1 to the power of n times m minus 1 divided by n times something we'll call BIM of boldface 1 minus x divided by m factorial, where this boldface 1 is just the constant vector 1, and these b's are some sorts of Bernoulli polynomials, given as follows: BIM of 1 minus x divided by m factorial to the n is given by the coefficient of essentially this g, or an appropriate coefficient of this g. So in particular, coefficient of g evaluated at uy, then set yi equals 1 to make this function meromorphic at 0, so you can look at its Laurent expansion, consider its coefficients, and then we consider the coefficient of the term u to the n, y1, skip yi, yr, all to the m minus 1. Okay, and this is very much like what you would do for the Riemann zeta function to get the values at non-positive integers in terms of Bernoulli numbers. So let's do an example, especially because it's important from the point of view of Stark's conjecture. Let's look at the value at 0. Okay, so let me call this integral here. Let me call this I epsilon of s, I guess. So let's try to evaluate I epsilon of 0. Well, this is going to be now the integral du over u over the Hankel contour 0 infinity epsilon of the integral over this other Hankel contour raised to the n minus 1 of g of uy setting yi equal to 1 times 1 over y1 skip yi dy1 skip dyi dyr. And note from the formula here that, or this was sort of the point of these substitutions, t equals uy, that g, for a fixed u, g is holomorphic within the polydisk part of this copy of this product of n minus 1 copies of the Hankel contour. So all we're going to get here is we'll use the residue theorem n minus 1 times, and we'll get the constant term of that series. So what we'll get is 2 pi I to the n minus 1 from the residue theorem of the integral over the Hankel contour C of infinity epsilon du over u. And now we just evaluate this at all the y variables equal to 0, except for the ith one, which we're setting equal to 1. So what we'll get here is the product, as j goes from 1 to d, of e to the u ai j times 1 minus xj divided by e to the u aij minus 1, and this is integrated. I already have my differential there. And now this is an expression that looks like a product of generating functions for the Bernoulli polynomials. In fact, that's exactly what it is. And so note that this product occurring in the integral, we can rewrite it as the product as j goes from 1 to d of 1 over u times aij times u aij times e to the u aij times 1 minus xj divided by e to the u aij minus 1. And now this is exactly the generating function for the Bernoulli polynomials. So what we get is the product as j runs from 1 to d of 1 over u aij times the sum as k runs from 0 to infinity of the kth Bernoulli polynomial evaluated at 1 minus xj divided by k factorial times u aij to the k. Maybe I should index my k by the j. All right, so in this way, and now all we're integrating against u is a power series in u, well, divided by u. So again, the value at 0 by the residue theorem is just given by the constant coefficient of this power series. And I'll just write ... for the rest of the calculation and give you the answer. And what we get is that zi of ax0 is minus 1 to the d divided by n times the sum over partitions of the integer n into non-negative parts of the product as j goes from 1 to d of blj of xj divided by lj factorial times aij to the lj minus 1. So this is what you get at the end of the day. Yes. That's just maybe just over tuples L1, LD. Okay. Now, so you get a sort of a cheap corollary from this, that this value belongs to the field generated by the coordinates of x and the matrix entries of A, right? Because the Bernoulli polynomials have rational coefficients. So what we get is that zi of ax0 belongs to the field generated by the xj's and the aij's. And in the situation where all of our data comes from a number field, everything here is algebraic. So in particular, we have a proof that the special value at 0 of the zeta function of a number field belongs to that number field. But you can actually do a little better. Well, you can give Shintani's proof of the Klingon-Ziegel theorem that the values of all these partial zeta functions we've been considering are actually rational. And the way this happens is when you end up summing over I in the situation where you're working over a number field, because the I is indexed, the embeddings of our field into its Archimedean completions, all you get is a trace. So the formula is, so really the proof of this, and this proof is due to Shintani, that well, the upshot of the proof is the following formula: zeta ax let me just give it for the value at 0, and let's suppose that all the, that all the columns of A arise from points in our number field with which are positive under each real embedding, and what we get is the sum over these ordered partitions L of the trace from F down to Q of the following quantity, the product now as J runs from 1 to D of B Lj of Xj over Lj factorial times Aj to the Lj minus 1. And in the situation where we're trying to relate Shintani zeta functions and partial zeta functions of number fields, these xj's are all rational. There's coordinates of certain vectors. So this is a rational number, it being the trace down to Q. Now, these kinds of quantities come up a lot, especially in our group project. These quantities are sometimes called Dedekind sums. So really what Shintani did is show to give a systematic way of writing special values at negative integers of partial zeta functions in terms of, these Dedekind sums that he defined. These are more general than the version considered classically. Okay, so this is Shintani's proof, essentially, of the rationality of partial zeta values at negative integers. And by the way, if your field happens to have a complex place, then gamma factors in the functional equation are going to force all of these points to vanish, so you aren't saying anything interesting, except for in the totally real case. But we are interested in the non-totally real case from the point of view of Stark units. In particular, we're interested in producing Shintani zeta functions for ATR fields, and for that reason I need to discuss a bit of what to do, a bit of subtlety involving the theory of Shintani zeta functions in the non-totally real case. So let me just set up a bit of notation. Sum is exactly the same as we've used before, so let F be now an arbitrary number field, and let's let Vi be the real embeddings of F from, say, I goes from 1 to R1, and Vi will be the complex embeddings of F for I going from R1 plus 1 to N, and we'll take an ideal of F and look at the corresponding narrow ray class field. And the theorem I stated yesterday was, well, the result due to Shintani, that there exists a finite collection of cones such that the positive part of F can be decomposed as sums of translates by totally positive units congruent to 1 mod F of the cones in C. So sum over the disjoint union over epsilon in E of F of the union over cones in my collection of epsilon times C. And my cone C has a representation of the form, the sum of non-negative rational numbers times some element of F, of the positive part of F, and I'll just index it by a C to say that I get these A's for each cone in my decomposition, and this runs from J up to the dimension of the cone C. All right, so this is some notation I'll have use for. Now the problem is, when you're choosing such decomposition, then there's really no guarantee that the real parts of these A, C, I, J, sorry about the lots of indices, that these have positive real part. And there's a fix for this. It may seem a bit ad hoc, but we'll see in a little while that there's actually some content to this. It'll come into play in a fairly major way when we discuss the Stark unit constructions. The fix is that at the cost of perhaps refining our decomposition, meaning refining each cone in C, there exist complex numbers which I'll index UCI, indexed by cones in C and I indexing the embeddings of our number field, such that the following properties hold. First of all, that UCI is 1 for all I. So if I happens to be an index of a real embedding, then, well, we're really just going to say this is going to be 1. Secondly, if VI and VI prime are conjugate complex embeddings, then the corresponding complex numbers that we're asserting the existence of are complex conjugate. And third, and most importantly, that the real part of UCI times AIJ is positive. So we can fix this positivity condition by introducing these UCIs, which you can think of as somehow rotating each cone into the part of the positive part of F where everything has positive real part. ACIJ, yes, thank you. Now, what I'd like to observe here, well, first let me introduce a piece of notation. Let me put all these U's into a matrix. So it's perfectly fine to just assume that the U's are all 1 for the real embeddings. And let me just put them all into a diagonal matrix. Then this property 2 actually implies that if you just look at the Dirichlet series formula, well, not the zeta function yet, that the norm of UCAC times x plus k is equal to the norm of AC times x plus k, because you're just multiplying the norm multiplies all the entries, and you're multiplying each entry by the corresponding UC, and the product of all of them is 1, thanks to the fact that they're either 1s or complex conjugate numbers on the unit circle. So in particular, it makes sense now to write that zk over fs of sigma a s is a sum of Shintani zeta functions that now makes sense. So we can sum over cones in our collection, and then we can sum over points over coordinates of points in the fundamental parallelograms of these cones. So we'll say z varies over 1 plus a inverse f intersects c. Z has coordinates xj, xj, aj, and these xj's are between 0 and 1. And what I'm going to sum are these Shintani zeta functions UCAC x s. And now this makes sense because all the entries of these have positive real parts by design. And I'm not affecting the identification with the partial zeta function because of this trivial identity. What I'd like to do is, so now I need to define the corresponding decomposition of this partial zeta function in terms of Shintani's decomposition of Shintani zeta functions. So let me define zi, and I'll put a few parameters here on the dependence of which we'll analyze shortly. So we'll sum over all cones, and we'll sum over all the z's in the fundamental parallelogram of these cones. And now, instead of just taking the zeta function, I'll take the ith piece of it. And then I guess this depends on, so this will be now depending on A and C, and this choice now of these complex numbers UC. Right, so we have a decomposition of, oh, sorry. That was circular. Okay, that makes sense. Good. And what we have now, just putting these two formulas together, is that the partial zeta function, zeta k over f, associated to the Frobenius of A at the point S, is just the sum, as I goes from 1 to n, of zi, and I'm going to be really careful about the dependence of this zi on its parameters. So keep writing the A and the C and the UC and the S. Okay, so let's look at an example for a moment. Let's consider the case where f is an imaginary quadratic field. Yes, let me put that here. Okay, so let me take my imaginary quadratic field f, and what I'll want to do is, well, Stark's conjecture says that zeta k over f prime sigma a 0 will be minus the log of the absolute value of the Stark unit, twisted by sigma, and so this is for all sigma in the Galois group of k over f. And recall that our goal was to decompose this and get rid of the absolute value sign. So this, we should write this as minus the log of u sigma plus the log of u sigma bar, w of this and w of that, to make them complex numbers whose conjugate I can take. And now we have some candidates for what these could be. So it's tempting to say, okay, this is z1 primed at 0, and this is z2 primed at 0. And in fact, this is the case, and these quantities z1 primed of 0 and z2 primed of 0 don't depend on any of these choices we've made. And so what we get is that elliptic units can be recovered by Shintani's method, and this was actually pointed out by Shintani himself. He proved that, say, z1 prime of all this data evaluated at 0 is the log of a CM value of a Siegel unit. All right, so this connects explicitly Shintani zeta functions and the classical CM theory of imaginary quadratic fields. And we'll see in a little while why, in this imaginary quadratic case, this is independent of all the choices we've made. And hopefully we can generalize this kind of decomposition and the application of it to construction of units to other more exotic ATR fields. Say, complex cubic fields are the ones I have in mind for the moment. But it's important to realize that if n is bigger than 2, then these quantities zi prime of A, C, UC collection 0, this is not independent of our choices. So it's dependent on our choices, you could say. So in the next section, I'd like to analyze the dependence on these choices to try to see what a canonically defined quantity could be that might have something to do with our Stark units. So let's analyze the dependence on choices. And let me summarize these dependencies in a theorem. So we'll analyze the choices and then adjust our first candidate, zi prime of 0, accordingly to make it well defined and hopefully come up with a unit. So here are the dependencies. First of all, if we look at zi of AC, the u's at 0, so the value at 0, then this is well defined. The value at 0 is independent of all our choices. Secondly, if VI is real, then we're in good shape, and we really haven't had to rotate anything. So it's not particularly surprising that in this case, zi prime of A, C, UC, 0 is also well defined, independent of all our choices. Things get more interesting when we consider a complex place. Let's move on to 3. So let's suppose VI is complex. Then let me let n of Cx be the denominator of zeta of UC AC x 0. You've seen this as a rational number in the first section of the talk, and we can consider its denominator, which will unfortunately come into the picture. Then the dependence. Well, let's first look at the dependence on the choices of these complex numbers u. Let me define phi of AC x to be zi prime of UC AC x 0 minus zeta times UC AC of x 0 times the logarithm of this complex number UCI. So although this derivative isn't independent of our choices of these u's, if I take off this correction factor, which involves the logarithm of that complex number and this rational number, then this is independent. This is independent of maybe I would like to phrase this differently. Sorry about that to the note takers. Then I'd like to say that the congruence class phi ACX modulo 2 pi iz divided by this n of Cx. This is well defined. So this number isn't well defined absolutely, but it's well defined modulo this lattice commensurable with 2 pi iz, which is the lattice of ambiguity when you specify the argument of a complex number. And since what we're going for anyway is trying to find the logarithm of a unit, right? Really, the argument, it's not surprising that this ambiguity in the argument comes into play, because what we're seeking is actually a logarithm. But what is annoying is this denominator, and I'll make a few remarks about that in a moment. But first, let's put all of these little phis together. Let me define big phi of AC to be the sum over all of our cones of the sum over all these points in the fundamental parallelogram associated to the cone of phi AC x. And let's set n AC to be the LCM of the finite number of quantities n cx, where these cx's are the ones that appear in the above summations. And it follows immediately from 3 that phi of AC mod 2 pi I over n of AC z is well defined, or is independent. is independent of UC. All right, so still not independent of our choice of covering or our ideal representative of our ideal class, but we'll knock these dependencies off one at a time. And in addition, essentially by construction, these terms will cancel because they appear when you add them all up over to the when you sum over I, you'll get the non-zero terms here appearing with their conjugates. So what we'll have is that the sum of these phi i's, as I runs from 1 to n, is the quantity we care about, zeta prime k over f s of sigma a 0. All right, now let me do some marketing. What I think would be a worthwhile project if you wanted to get to know these Shintani type methods and their application to start conjecture is to get rid of these annoying denominators. They're especially annoying because they actually depend on these choices, right? So somehow what we get at the end of the day isn't going to be as well defined as we might like. But you should be able to get rid of these denominators by the process called smoothing. Sam is going to talk about this more in his lecture tomorrow in a slightly different context, but this is an important technique in the theory of, say, p-adic L functions. It involves making your zeta values integral by taking certain combinations of them. All right, and this allows for interpolation in particular. But the problem here is that these zeta values which arise aren't integral. But if we take appropriate combinations, then we should be able to achieve this integrality. So, and then you'd like to t-smooth this whole discussion. And, well, in the following 10 minutes, I'll describe the connection with Stark's conjecture involving this zeta value. But what you want to do in this case is relate it to the Stark-Tate conjecture, which Samit stated in the first lecture. It's equivalent to the Stark conjecture, which says that zeta prime k over f s t of 0, where t is an auxiliary set of primes, is equal to minus the logarithm of ut sigma w. And in this situation, the ut is unique if it exists. Okay, so this wouldn't be the first time that the smoothing technique has been applied in the context of Shintani's method. It was used, for instance, in Casaunuguez's construction of the p-adic zeta function. Of totally real fields. And this technique was also used in Dasgupta's refinement of the Gross-Stark conjecture. Right, so the smoothing technique has been applied successfully in several well-known instances, and I'm reasonably sure it's equally applicable in this case. And that would make all the formulas much nicer. And being optimistic, I'm going to now ignore all the n's, just to make my life a little simpler. So although it might be a little dubious, I wouldn't go so far as to call it bogus. Did I finish that? All right. So we've dealt with the dependence on these complex numbers u, which was a little more subtle than one might have expected from first glance, let's now consider the dependence on our covering. So let's suppose that Vi is complex and that we have C and C prime, two different coverings. And the comparison we can make is the following. There exists a unit, epsilon, in E of F, the totally positive units of the base field congruent to 1 modulo F, such that phi of A C prime is congruent to phi of AC plus log of the image under the ith embedding of this global unit epsilon, and this is mod 2 pi I z, and so here I'm not writing n. So let me give an indication of the proof of this, because it might seem sort of surprising that a global unit is intervening here. So let me show you where that comes from. So the first remark, and this is, I'm sort of burying the lead here, this is not an easy thing to prove, is that that phi of AC is invariant under subdivision of C. Right? So it's not invariant, it's not independent of all choices of cone decomposition, but if you fix one and just refine it, you aren't going to change these values. And this is a fascinating argument due to Sheck, and I think I have those constants in the right order. Okay. So thanks to this result, it suffices to consider the following situation. The situation where for every cone in our covering C, there exists a unit, epsilon sub C, in E of F, such that C prime is just the set of all translates of the cones in C by these units epsilon. Right? They have to be they're fundamental domains for the same thing, right? And you can subdivide to your heart's content so that the simplices match up in a one-to-one way under the action of the group that's tiling this region. Okay. What we have to compare are the data associated to C and C prime. So, what we have is that the matrix of generators of the cone epsilon CC is nothing more than a simple matrix delta C times the matrix associated to C, where delta C is the diagonal matrix consisting of epsilon 1, epsilon n, I should certainly have C's here. And we can take U epsilon C C to be UC times delta C inverse. So the matrix which ensures positivity of my matrix elements for this cover C prime, I can define in terms of the corresponding data for C, because, well, delta is just a diagonal matrix consisting of whose entries are totally positive units. And using the results of the previous theorem, so now we're in a situation where really we're back to considering the dependence on these rotation matrices, on these U's. So we can use our previous results and conclude that phi of A epsilon CC x, and then if I subtract from that zeta of U epsilon C C A C, sorry about the multiple layers of subscripts, x0 times the logarithm of UCI epsilon CI inverse, which is the ith diagonal entry of UC delta C inverse. This is going to be congruent to phi of ACX minus zeta of UCAC x0 log of UCI I. UCI just UCI. I don't think I need that either. Okay, and the values at 0 we pointed out are independent of our rotation matrices, so these things are actually equal. So what we're going to get is, when we express the logarithm of this product as a sum of logarithms, we're going to get the terms involving the UCI's canceling. And so what we conclude is that phi of A epsilon C C will be congruent to phi of AC, I missed an X here, sorry, ACX, plus, let me write it in this way, the logarithm of epsilon C I to the power of zeta UC ACX 0. All right, I'm more or less assuming this is an integer. If not, I have to fudge it with some n's, but here we have the logarithm of the ith embedded version of a global unit, and now sum over I, or sum over x, c, etc. All right, and then just combine all these terms into a product of one massive unit, and that's our epsilon. All right. So we've analyzed the dependence on the matrix, on the complex numbers U. We've analyzed the dependence on the cone decomposition C, and I'm going to just state that you can analyze the dependence on the ideal A in a similar way and get to the point, which is the case of complex cubic fields. Or we can actually do something explicit. Involving unit constructions, and this construction is due to Ren and Sech. So what we're going to take is F to be a complex cubic, and we'll let V1 be the real embedding, and V2 and V3 will be its two complex conjugate embeddings, and it's an essential feature of the way I'm going to describe it, that E of F is, well, it's a rank 1, it's a unit rank 1 situation. And let me assume that our conductor F is chosen so that there are no roots of unity congruent to 1 mod F. What we want to find is a quantity theta mod 2 pi I Z, which is some combination of phi1 of AC and phi2 of AC, such that two things happen. First of all, theta mod 2 pi IZ does not depend, is well defined, does not depend on A or C, and secondly, we'd like minus theta plus theta bar to be equal to zeta k over f s prime of sigma A 0. If we can define a complex quantity theta which satisfies these two criteria, then it's reasonable to conjecture that this theta is actually the log of a Stark unit. So the conjecture in this case, well, you can do this, I'll show you how to do it in a moment, that the conjecture is that the theta, as we'll construct it in a moment, is the logarithm of a Stark unit. So in particular, if you can compute this quantity theta by using numerical methods involved with these Shintani decompositions, you could actually compute the Stark unit just by exponentiating, because the absolute value is nowhere in sight. And you might wonder why I only wrote phi1 and phi2 here. The whole point of this method was we only needed to consider one embedding. We only wanted to consider one embedding out of each complex conjugate pair, and Stark's method does do this separation. All right, so I won't have time to justify these two claims, but I'll give you the definition. So we'll define theta to be phi1 of C A times the logarithm of eta 2 divided by the logarithm of eta 1 minus phi 2 of CA. Let me just state in words, the reason this is well defined is, well, the ambiguity in these phis involving the cover involved a unit in our number field. All right, but we put ourselves in a unit rank 1 situation. Right, so this ratio, if there's a corresponding rate, we look at this ratio is independent of the unit we pick, actually. Right, everything is a power of eta, so regardless of what this quotient is, regardless of what unit comes up, this quotient is the same, and that's the argument for it being well defined. And this argument, but let me give that briefly. Theta plus theta bar will be phi1 times the logarithm of eta 2 plus the logarithm of eta 3. That's the conjugate of eta 2 divided by the logarithm of eta 1. And then minus phi 2 minus phi 2 minus phi 3. And then if I bring these things to a common denominator, right, okay. So, yeah. Sorry, my mind is malfunctioning. I'll let you guys work it out. Punt.